Hey, Alyssa.
Hi.
How's it going?
Pretty good. How are you doing?
I'm doing all right.
I gotta go eat real quick. So I'm gonna stop video.
Sounds good.
Morning. I guess afternoon.
Good afternoon.
Zach, what's good, my guy?
My name's not Zach. Thanks, Noah.
Sorry, Connor. I saw you earlier, but Zach's my lab partner, so like it's different, you know?
All right. It's 12:30. Locking the door. Let's do this thing. Oh, Lord, thank you for bringing us together this afternoon. Thank you for everything that you do for us. I pray that you would help us get through this last week of being online, help everybody get back to campus safely, help us to continue this momentum forward through the rest of the semester and just keep learning, growing, and striving, Lord. In your name we pray. Amen. All right. Everybody's favorite topic today. Well, one of them. The next 4 weeks. 3 weeks? The next 3 weeks. We're going to be covering everybody's favorite topics. They're all here. Circuits, op-amps, fluids. It's all happening now, guys. It's all happening now. Everybody, I can hear the collective groans through the internet, even with you muted. It's something. It's a thing that's happening. All right, so let's take a look at this. Equivalent inertia homework. I'm unaware of any problem on the homework that required you to do equivalent inertia. Jeff, people are confused by Jeff. Jeff's a confusing guy, man. So this is what I want you guys to think about when you're making an effective inertia, if you are, because you're not required to, but if you were to make an effective inertia, why? Why do we do it? Right? Why? Because I'm trying to take two things, right, that are not the same, right? In this case, we were using 2 gears, and those gears are not rotating about the same axis, right? They're not. But you can combine both of them in such a way that they can be a new different thing. You would now have the inertia of those 2 gears as if they were spinning around the one axis that we're interested in. And that is why we would use an equivalent inertia, right? I know I promised you guys a video that I haven't done yet. I swear it's coming. It'll get up there eventually. I got bogged down, with lab reports and things to grade. So once the grading is off my table, I will make that video of that problem. Chaos. Chaos is when everything is just not happening in an orderly fashion. That's what that is. So just wait. Equations, name, assumption. All right. So hopefully if you had questions for last homework, you got them answered before turning it in. Right, last homework was due on Sunday. I have posted since then. So yesterday I posted the new homework, all the example problems from weeks 1 and 2. I still owe you a couple, which I'm going to go scan in my office right after class and put up today. So you'll have those and a new list of example problems for you guys to try for class. We'll get to those this week and next week. They'll kind of bridge the two weeks. The plan is that we will spend about 1.5 weeks on electrical and electromechanical systems, and then about a week on fluid and thermal systems. And then we have an exam coming up. Right? You guys have any other questions about stuff that I didn't get to? I feel like Jeff was the real sticking point for a lot of people last class. When do you know that you want to make an equivalent inertia versus not, right? Well, sometimes we just don't care about that contact force, right? We don't care about how things are spinning around the first axis, right? Because everything is being driven by that second axle, that second rod that's connected to the second gear, right? So why not just make everything simple and make it a single system, right? That's where that comes from. Okay, so if you guys don't have any other questions, we'll keep pressing forward then. All right, so here's some stuff. Let's do. This is going to cover us all the way through week 5. I understand that next week, well, this week is you guys will be trying to get back to campus and stuff. this week, and then next week it's finally happening, guys. It's finally happening. Half of you will be in here during Tuesday, and you will hear me yelling at you instead of at the computer at you, because I'm gonna have to wear a mask. So if you're in the room, it's probably still gonna be loud. I'm sorry. So half of you come Tuesday, half of you come Thursday. It's gonna be great, right? It's gonna be a fantastic time. We have an ethics paper due on Sunday. Say what? That's right. It's an ethics paper. What does this entail? It's a great question. Allow me to talk to you about it for a moment. You can always subscribe to my newsletter, and then you would be up to date on all of these things. I swear I won't sell your information to other companies. Anyway, what are we doing? Why is there an ethics paper? Great question. And I'm going to leave it there. So you need to review the article, which is on LoudCloud. It's called Beyond Proximity, Consequentialist Ethics and System Dynamics. And then you are to write an 800 to 1,000 word essay on the importance of ethics in the field of system dynamics from the perspective of the Christian worldview. Okay, what does that entail? Well, there's three real things that I'm going to be looking for, right? The first is, what ethical considerations should be examined when making a decision about a model from the Christian worldview perspective? You need to provide an example of a situation when a defective product went to market or was sold, and the ethical responsibilities of the decision maker to sell it anyway. The second thing is you need to, right? So the second question to be answered is, should a procedure be in place for making model boundaries? And you need to discuss a possible procedure for making an ethical decision. And third is it ethically wrong from the perspective of the Christian worldview to make assumptions about modeling, right? It says to use APA style guide, right, and all that. There is a rubric for this. Please take a look at the rubric, right, before you start doing things, and familiarize yourself with it. Okay, so I'll start off by saying this. I am not claiming to be, nor have I ever claimed to be, an expert in Christian worldview, right? I feel like I'm pretty good, but I'm not a doctor. I don't have my doctorate in theology, right? I'm not going to argue the finer points of Christian worldview perspective with you. I am not an expert in the ethics of model making and decisions, right? That is also not a field which I would consider myself well versed. However, I am, so my point is what? My point is, you can take whatever side of this argument you want. That is not what is in question here. What I'm looking for is, are you able to argue your point with research, right? So do you have sources to back up your opinions? That is what is important here, okay? So yes, you think models, you think that assumptions are immoral, right? You think that assumptions should never be made, or yes, you think it's okay to make assumptions, right? Either one of those sides that you pick is fine. Pick a side and argue your point. Okay? That's what I'm looking for. Just a quick note, some of you may have noticed, some of you might not have. You will see if you go into LoudCloud that my name is co-listed with Jose Valenzuela on our class. He is our grader. He is going to be grading the lab reports and the ethics assignments. I talked to him about what is expected, right? So, just so you guys are aware of that, I'm still grading homeworks and exams, but he's just going to be any written stuff. He's going to be taking care of it. Okay. Again, so if you get your grades back and your feedback, and you ask questions about it, you can always ask me questions. Right, I can always go in and look at your papers and stuff. But he's just going to be taking the grading for those things. Okay, just in the interest of being open and transparent. Right. Homework 2 is going to be due on the 4th. Exam 1 is on Thursday the 8th, and homework 3 is going to be due after the exam. Okay, it's going to be due after the exam. All right, so we've got a pretty heavy load coming up. It'll back off a little bit after that in terms of the amount of homeworks. I mean, it won't be like one a week. I try to keep it one every 2 weeks, but this brings us to the end of the modeling portion, right? That's what this does. All of these assignments. Okay. You guys have any questions on anything that's due? No. The lab reports should be graded soon, so just hang tight. All right. I'm starting homeworks today, so I'm hoping that by Thursday all the homeworks will be graded, but Friday at the latest, probably. Depends. Yeah.
Question on the ethicals assignment. Is there a required amount of citations or sources we need for it?
So my rule is you need to have as many as you need to have. I'm not looking for a specific number, but you have to have at least one. Okay. I mean, if you're going to read that paper, you should be really citing that paper at the bare minimum, right? And I've communicated that with the grader as well, right? He knows the things that are important for my style of grading, and he's trying to get us. We're trying to be in alignment, right? Because he doesn't grade all of my classes, just this one.
All right, thank you.
Okay. Any other questions? No? Then we will proceed. Instead of a gift today, we're gonna do this. I'm gonna switch that. We're gonna do this stuff. Don't worry about this guy for a second. It won't let me skip it though, so sorry. So this is the intro to electrical systems.
Can't see it. You're still on the assignment screen.
All right. So yeah, it's the electricity, guys. Electricity. Totally not a stretch, right? Totally not. All right. Thanks, Taylor. I know it's legit. Didn't rip it off. I came up with that, by the way. All right. So what are we doing?
That sounds like something you would write.
Electrical and electromechanical systems, right? What are we trying to do? Well, we're trying to create mathematical models of circuits using Kirchhoff's voltage and current laws, right? And the voltage and current divider rules and loop analysis, right? Also, we're going to do that ethics thing, right? So evaluate ethical implications of making assumptions in developing our models. All right, and so now this is the point where I say, I know guys. I know that some of you had GEM for circuits, okay? I know that this happened. The faculty know that he was here, believe it or not. We understand that. I know that a lot of you guys have a certain amount of scar tissue associated with this topic, okay? All right, I know. And look, you don't have to be afraid of him. He's not here anymore, okay? You can say his name. It's not like Voldemort, right? He said Voldemort. Okay. So anyway, I understand, right? But what we're really going to be doing with these models is we're going to be talking about how to use Kirchhoff's laws, right? So this should be stuff that even if you had Jenny, whoever came in to save the day after the fact, right, should have covered a lot of what we're going to be talking about. Okay. So it may surprise you guys to hear this, but electronic circuits and electromechanical devices are used extensively by both mechanical and biomedical engineers. I know. I'll wait for you guys to stop being shocked. I know. So that being the case, what are some examples? Somebody, anybody, feel free to unmute and say your favorite electronic circuit or electromechanical device.
Wheatstone Bridge.
Oh, that's a good one. That's a good circuit.
That's like the only one I remember.
Mhm. What do we use a Wheatstone bridge for? What's the most common application for using a Wheatstone bridge?
Strain gauge.
Strain gauge. There it is. What else? What else do we use? What's an electromechanical device that's very common that gets used quite often?
Like hydraulics, or what was the other? It was a pressure, like the actuators.
Sure. Like a
Yeah,
solenoid.
hydraulics would be the right word.
Solenoid valve, actuators, yeah. You guys all took ESG-250. There was something specifically that you used in ESG-250 that would have been a very common electromechanical device.
A switch.
Turbine.
You used a turbine in SolidWorks? Man, that class has changed quite a bit. You would have used it for your little car. Your little car had a
Motor.
yeah, it's a motor, right? Motor. All right. So we've all experienced some of these things, right? So just like a mechanical system, electrical systems have elements, right? But we have two flavors of elements with an electrical system, right? We've got passive elements, which are elements that don't introduce any energy into our system. These are things like resistors, capacitors, and inductors. They store or dissipate energy, but they don't add any more energy into our system. Then we have active elements, which add energy to our systems, right? These are voltage and current sources, right? So we've got sources and we've got sinks, essentially, right? We have sources that put energy into our system, and we've got these passive elements, which are your standard resistance, resistor, capacitor, and inductor. Right? So let's talk about those a little bit, right? We'll talk about each of these in turn. So we'll start with the resistor, right? And here in the top left corner, we've got a nice picture of what a resistor looks like on a circuit diagram, right? On a schematic. You'll notice we've got positive on the left, negative on the right, right? We've got E sub R written there. When we talk about the voltage drop across a resistor, we're going to use E sub R. So what does a resistor do? What does it do? What is it made for? This is a question for you guys, not rhetorical.
Limits the amps that can go through.
Yep, it hinders the flow of current and dissipates electrical energy by converting it into heat. Right? So what is this similar to in a mechanical system? What would this be equivalent to in a mechanical system? What's the analogy here?
It's like a nozzle.
So what element?
It would be the friction element.
Yes. So the damper, right? This works in the same way as a damper. It restricts the movement of current. A damper restricts the velocity, right? It restricts the force. Okay. Resistors are governed by Ohm's law. And so the voltage drop across a resistor, E sub R is equal to R, the resistance times the amount of current through that resistor, right? Remember that voltage drop is going to be volts, current is going to be amps, and resistance is going to be in ohms. Okay, so let's talk about a voltage drop. What is a voltage drop, right? If you were to take a multimeter and hook it up on either side of a resistor, what are you actually reading? What is that value that comes out? Right.
Potential difference.
Difference, right?
Yeah, it's the difference, right? It's the difference of, so a voltage drop tells you how much voltage you've lost, right? It tells it essentially, right? The voltage drop is how much is coming in minus how much is coming out, right? And that's going to be important later in class. So keep that one in your mind for a little bit, right? Because we can rewrite certain equations in terms of that. All right. What about power? Right, as we talk about the power, well, the power dissipated by a resistor, zeta dot R, is minus ER times I, or negative RI squared. That is how much power your resistor will eat, right? And look here in the red box, there's the ideal linear resistor equation, right? That is our element equation here. Right? This is the equation that we will be writing for our mathematical choice. Right? What is it? It's just Ohm's law, right? It's just Ohm's law. Another way of thinking about E sub R, just this is the same as delta V across my resistor, right? Delta V across. So that's a nice linear relationship, right? It's really nice. So we're good with resistors, right? Everybody feeling all right with this? So we're going to use Ohm's law, and we might use that power, but we're probably not, right? When would we use that? We'll talk about that when we need it. We don't need it for anything right now. Okay. So that's going to lead us into the capacitor. I'm going to move this just right here. Okay. So you see in the top right corner, we've got a picture of some real life capacitors, right? And then just below it is the symbol from a circuit diagram of what we would draw a capacitor to look like, right? So what is it? What is a capacitor? And what is it meant to do?
It's like a gap.
Stores energy.
There you go. Right. So it's like a gap and it stores energy. That's true. It is like a gap. What is it? It's two conductors separated by a dielectric or an insulator, right? And so when we draw it like this in our diagram, we have two parallel plates, the black lines, and inside, right? The way that I always like to think about it is we're trying to fill the capacitor, right, with charge. And then once it's full, then it becomes, that's when we connect both sides of our circuit. All right, so what does it do? We said it stores energy, right? So since it stores energy, what is the analogous mechanical element for a capacitor?
Battery.
Remember, we're talking about what is it in a mechanical system?
A spring.
Spring. No, it's actually an inertia element. We're gonna go through. We're gonna watch a video that ties it all nicely together. But in our systems, the capacitor is like an inertia. The reason why is because how the variables how it stores energy. Right? It's about how it stores energy. Okay. So in our system here, right, we have a charge voltage relationship for a capacitor, which tells us that the amount of charge is equal to the capacitance times the voltage drop across that capacitor, right? Which is great, but we don't normally measure charge, right? We don't normally measure charge, but something we do measure is current. And current is the time rate of change of charge. So Q dot is equal to I, which is equal, if I take the derivative of this equation, to C E dot C. Okay. So I said it has to do with the energy storage, right? And we'll get there in a second. But let's talk about the voltage drop. Now that looks like a fun equation, right? Yeah. So if you wanted the voltage drop across the capacitor, right, you'd have to integrate this equation, yes? And that's fine. We could do that. But you'll see that we're not going to really throughout the class. Because we're gonna, instead of doing that, we're gonna leave it in this format here. And then later, when we do Laplace transforms, we'll take care of the integration. All right. So the energy stored in a capacitor, right? Energy stored in a capacitor. Well, the energy is zeta sub c, and that's 1/2 CEC squared. So the voltage here is squared. Now I told you, I said that this behaves, it stores energy like an inertia, right? An inertia stores things as kinetic energy, kinetic and potential. Well, this looks kind of like kinetic energy equation, right? 1/2 CE squared. Well, if we're talking about it being equivalent to an inertia, velocity and voltage are equivalent in the way that we discuss them and how they behave in our systems. And this has to do with whether it's an across or a through variable. And the easiest way to think about this is that we always talk about the voltage across an element and the current through. Okay? And think about this with a spring, right? Think about this with a spring or a damper. The force doesn't change through the damper. What changes is the velocity. Okay. So if we take the derivative of that, we can get the power. Right? The power is C, E dot C times EC, right? Punchline, right? What's the punchline? Here it is, right? You'll notice that I will stop from this point on. You will never see this Q dot ever again. I will write it as I is equal to C E dot C. That's how I roll. This is the fundamental capacitor ODE. This is our mathematical truth for our capacitor element. And again, remember, this assumes that we're using ideal elements, right? So it's just a capacitor. It doesn't do anything else. It's a unitastic. Cool. Okay. What else we got, right?
I have a
All right.
question, actually. Sorry to interrupt. So the E dot C is current, right?
So
E dot subscript C.
this E dot here, that's the rate
Yeah.
of your voltage drop, Trevor.
The rate
I is current.
Oh, okay. That's what I was gonna say, because I'm like, wait, I is current. Why would that be? So it's the rate of change for the voltage drop?
Yeah.
Okay, thanks.
Yeah. Any other questions? No? Okay, we'll keep going. So that's resistors and capacitors. And if you thought to yourself that that leaves inductors, then you nailed it. Notice the inductor in the top right corner of your screen. I'm pointing there right now. Actually, my picture is probably on top of it, right? So move my picture. Well, what does it look like? Well, kind of. All right, so even if you don't have that one, the top left corner over there, right? You will notice an actual real life inductor. And what does that look like?
The spring.
Looks like a spring. And so once again, we're going to say that so the only element left, right, to be analogous with was the spring. So inductors store energy in a magnetic field that is created by current flowing through the inductor. Inductors are going to be really important when we start talking about electromechanical systems, because the way that we generate a magnetic field that enables us to couple an electrical and a mechanical system together is the inductor, right? That's how we're going to do it. All right, so for an ideal inductor, we can say that the magnetic flux is equal to the inductance times the current through that inductor, right? Where flux is measured in Webers. Well, great. But again, we don't normally talk about magnetic flux when we're putting things together, right? So how do we deal with that? Well, Faraday's law for induction says that a coil of wire will have a voltage difference induced across it if the magnetic flux is changing with time. So if you have the derivative of the flux, this will create a voltage, E sub L, right? This will create a voltage drop. So lambda dot is equal to E sub L. And if I take the derivative with respect to time of lambda is equal to L I sub L and substitute in E sub L for lambda dot, I get this guy, right? And we can see that's our energy storage again, right? Where zeta sub L is 1/2 Li squared L. And zeta dot L, the power is L I sub L I. And again, here's our punchline. You guys were thinking this is gonna happen, right? There's gonna be a red box with the, I know I should have made it a purple box. I don't know what I was thinking. I apologize. Don't report me to the color committee, please. All right, so the voltage drop, and you'll, again, I will never write lambda dot. You will not see that lambda dot again, right? We are concerned with the voltage drop across the inductor, L I dot L, right? And this has a fixed inductance. Now, in the real world, sometimes you get a variable inductance, depending on how much of the way you are through a field. So just keep that in mind. But for ideally, our constants are fixed. Right. So we got an equation for a resistor, we've got an equation for a capacitor, and we've got an equation for our inductor. Right? We've got our three elements. Right? We've got our three element equations. Okay. What now? What now? Well, before we get into that, let's watch a video about how inductors.
Hey there guys, Paul here from the engineeringmindset.com. In this video, we're going to be looking at inductors to learn how they work, where we use them, and why they're important. Remember, electricity is dangerous and can be fatal. You should be qualified and competent to carry out any electrical work. So what is an inductor? An inductor is a component in an electrical circuit which stores energy in its magnetic field. It can release this energy almost instantly, and we'll see how it does that later on in this video. Being able to store and quickly release energy is a very important feature, and that's why we're going to use these in all sorts of circuits. Now, in our previous video, we looked at how capacitors work. Do check that out if you haven't already, links down below. So how does an inductor work? I want you to first think about water flowing through some pipes. There is a pump which pushes this water, and the pump is equivalent to our battery in the circuit. The pipe will split into two branches, and the pipes are equivalent to our wires. One branch has a pipe with a reducer in it, and that reduction makes it a little harder for water to flow through it. So the reducer is equivalent to resistance in our electrical circuit. The other branch has a water wheel built into it. The water wheel can rotate, and the water flowing through it will cause it to rotate. The wheel is very heavy though, so it takes some time to get it up to speed, and the water has to keep pushing against this to get it to move. This water wheel is going to be equivalent to our inductor. When we first start the pump, the water is going to flow, and it wants to get back to the pump as this is a closed loop. This is just like when electrons leave the battery, they flow and try and get back to the other side of the battery. By the way, in these animations I use electron flow, which is from negative to positive, but you might be used to seeing conventional flow, which is from positive to negative. Just be aware of the two and which one we're using. So as the water flows, it reaches the branches and has to now decide which path to take. The water pushes against the wheel, but the wheel is going to take some time to get moving, and so it's adding a lot of resistance to the pipe, making it too difficult for the water to flow through this path. Therefore, the water will instead take the path of the reducer because it can flow straight through this and get back to the pump much easier. As the water keeps pushing, the wheel will begin to turn faster and faster until it reaches its maximum speed. Now the wheel doesn't provide almost any resistance, so the water can flow through this path much easier than the path with the reducer in it. The water will pretty much stop flowing through the reducer and it will all now flow through the water wheel. When we turn off the pump, no more water will enter the system, but the water wheel is going so fast it can't just stop, it has inertia. As it keeps rotating, it will now push the water and act like a pump. The water will flow around the loop back on itself until the resistance in the pipes and the reducer slows the water down enough that the wheel stops spinning. We can therefore turn the pump on and off, and the water wheel will keep the water moving for a short duration during these interruptions. We get a very similar scenario when we connect an inductor in parallel with a resistive load such as a lamp. This is the same circuit as we just saw, but I've just wired it more neatly. When we power the circuit, the electrons are going to first flow through the lamp and power it. Very little current will flow through the inductor because of its resistance at first is too large. The resistance will reduce and allow more current to flow. Eventually the inductor provides nearly no resistance, and so the electrons will prefer to take this path back to the power source rather than through the lamp, so the lamp will turn off. When we disconnect the power supply, the inductor is going to continue pushing electrons around in a loop and through the lamp until the resistance dissipates the energy. So what's happening in the inductor for it to act like this? Well, when we pass electrical current through a wire, the wire will generate a magnetic field around it. We can actually see this magnetic field by placing compasses around the wire. When we pass a current through the wire, the compasses will move and align with the magnetic field. When we reverse the direction of the current, the magnetic field reverses, and so the compasses will also reverse direction to align with this. The more current we pass through the wire, the larger the magnetic field becomes. When we wrap the wire into a coil, each wire again produces a magnetic field, but now it will all merge together and form one large, more powerful magnetic field. We can see the magnetic field of a magnet just by sprinkling some iron filings over the magnet, which will reveal the magnetic flux lines. When the electricity supply is off, no magnetic field exists. But when we connect the power supply, current will begin to flow through the coil, so a magnetic field will begin to form and increase in size up to its maximum. The magnetic field is storing energy. When the power is cut, the magnetic field will begin to collapse, and so the magnetic field will be converted into electrical energy, and this pushes the electrons along. In reality, it's going to happen incredibly fast. I've just slowed these animations down to make it easier to see and understand. So why does it do this? Well, inductors don't like changing current. They want everything to remain the same. When the current increases, they try to stop it with an opposing force. When the current decreases, they try to stop it by pushing electrons out to try and keep it the way it was. So when the circuit goes from off to on, there will be a change in current. It has increased. The inductor is going to try to stop this, and so it creates an opposing force known as a back EMF, or an electromotive force. This back EMF opposes the force which created it. In this case, that's the current flowing through the inductor from the battery. Some current is still going to flow through though. And as it does, it generates a magnetic field which will gradually increase. As it increases, more and more current will flow through the inductor, and the back EMF will eventually fade away. The magnetic field will reach its maximum and the current stabilizes. The inductor no longer resists the flow of current and acts like a normal piece of wire. This creates a very easy path for the electrons to flow back to the battery, much easier than flowing through the lamp. So the electrons will flow through the inductor and the lamp will no longer shine. When we cut the power, the inductor realizes that there has been a reduction in current. It doesn't like this and tries to keep it constant, so it's going to push electrons out and try to stabilize it. This will power the light up. Remember, the magnetic field has stored energy from the electrons flowing through it, and it will convert this back into electrical energy to try and stabilize the current flow. But the magnetic field will only exist when the current passes through the wire, and so as the current decreases from the resistance of the circuit, the magnetic field collapses until it no longer provides any power. If we connected a resistor and an inductor in separate circuits to an oscilloscope, then we can visually see the effects. When no current flows, the line is constant and flat at 0. But when we pass current through the resistor, we get an instant vertical plot straight up, and then the flat line continues at a certain value. But when we connect an inductor and pass current through it, it will not instantly rise up. It will gradually increase and form a curved profile, eventually continuing at a flat rate. When we stop the current flowing through the resistor, it again instantly drops and we get this sudden vertical line back down to 0. But when we stop the current through the inductor, the current continues and we get another curved profile down to 0. This shows us how the inductor resists the initial increase and also tries to prevent the decrease. By the way, we've covered electrical current in detail in a previous video. Do check that out, links down below. What do inductors look like? Inductors in circuit boards will look something like this. Basically just some copper wire wrapped around a cylinder or a ring. We do get some other designs which have some casing over. This casing is usually to shield the magnetic field and prevent this from interfering with other components. We will see inductors represented on engineering drawings with symbols like these. Something to remember is that everything with a coiled wire will act as an inductor. That includes motors, transformers, and relays. So what do we use inductors for? We use them in boost converters to increase the DC output voltage while decreasing the current. We can use them to choke an AC supply and only allow DC to pass. We can use them to filter and separate different frequencies. And obviously we also use them for transformers, motors, and relays. How do we measure inductance? We measure the inductance of an inductor in the unit of Henry with a capital H. The larger the number, the higher the inductance. The higher the inductance, the more energy we can store and provide. It will also take longer for the magnetic field to build and the back EMF will take longer to overcome. You can't measure inductance with a standard multimeter, although you can get some models with this function built in, but it won't give you the most accurate results. That might be okay for you, it depends what you're using it for. To measure inductance accurately, we need to use an RLC meter. We simply connect the inductor to the unit and it will run a quick test to measure the values. Okay guys, that's it for this video, but to continue your learning, then check out one.
All right, so that's how inductors work, right? Like I said, inductors, their ability to create magnetic fields allows us to manipulate physical objects, right? And that's how we're going to be able to couple our electrical and our mechanical systems. Right? So resistance doesn't want any cake. Inductance will have a little bit of cake, and capacitance, you eat the whole cake. Okay, we already saw this one, but I just like this picture. So yeah, feel like the resistance is Australian because of the hat. That's just me. Anyway, let's talk about sources. Sources, right? So we've got two kinds of sources. We've got a voltage source and we've got a current source. So what's the difference? Well, here it is. The voltage source in an ideal is, so it's an ideal voltage source. And what it does is it will always provide the amount of voltage we say it's going to provide, regardless of how much current it needs to draw to do so. An ideal current source provides the specified input current at all times, regardless of how much voltage is necessary to produce said current. The difference here being that for a current source, you will be told the direction in which it is flowing around the loop, right? The current source has an arrow in it. For a voltage source, the typical convention is that you would travel from the positive node around. We'll use standard convention electron flow. Okay. That's it for sources, right? That's it for sources. We're not going to get into any other sources for electrical systems. Could you have like a sinusoidal source, like a wave generator? Sure, sure. But we're just going to stick with voltage and current sources.
So are we always going to be dealing with direct DC, not AC, or?
Good question. For now, yes, DC. Once we get to once we get to frequency response, that's when we'll talk more about sinusoidal inputs, right? Which is more like what you see with AC, right? Because it is AC is a sine wave. All right. So I told you we're gonna watch a video where we explain where these things come from and where to derive some things. I just want to preface this by saying I don't want you to feel overwhelmed like I'm expecting you to be able to do what they're going to do here. What they're going to do here is a very powerful tool, but it's not something that is necessarily it's not something that I'm going to test you on or have you do, right? But you're going to see, I'm hoping by the end of this video, you'll see why being able to jump between systems is a powerful thing, okay? So let's go over where these analogies.
It's
I have a
possible
question
when talking
before
about
we start
mechanical
this.
systems and electronic circuits to develop.
Yeah, what's up?
So if we're relating all these things back to the mechanical analogs, I get how the voltage source would be kind of like the equivalent of a force. But if you said it, I missed it. Is there like a mechanical analog for the current source?
So yeah, Taylor, actually, and I didn't mention it, but thank you for bringing it up. Current is actually force in our analogy, and voltage is velocity.
Okay. All right.
That's what we're rolling with. And you'll see why that is in a sec in the video.
Develop analogs between them. So if you remember, across variables, such as velocity and voltage, can be related with through variables, force and current, through various variables. And we have differential equations that allow us to turn cross variables into through variables. So also remember that the dynamical system has a behavior that's described by its equations of motion. So the motion of some mass inside a dynamical system has to obey the differential equation, the ODE that describes it. So that's the equation of motion. So here's an idea. Let's say that we have some equation of motion, and we have it for a dynamical system, well, a mechanical system. So what circuit would have the equivalent equations of motion? So this would be an interesting way to see whether you really understand what the fundamental topics are. But I have to warn you, some of the analogies that are made are not that easy to understand. So you have to go to the math first and then move from the math to your deep understanding. So let's begin with a couple of atomic examples. So the very first one that I'm going to have is a force that pushes on this mass m1, and we've indicated direction of motion here with x1. So you may remember that we have F as m1 x1 double dot. So force is mass times acceleration here because direction of motion is indicated by x1. Direction of acceleration is x1 double dot. So this is an extremely simple example. But clearly if you kept pushing with this force and there was no resistance, eventually the mass would be going really fast, right? And eventually it would, do things that it's not supposed to do. So we can also rewrite this as m1 v1 dot instead of x1 double dot. Because v1, of course, is x1 dot. So v1 dot is x1 double dot. So now let's go into the twilight zone. Here we're going to actually talk about circuits using the same kinds of variables. So the first equation that I want to write is I is equal to mass times the rate of change in time of voltage. So I've used force as a through variable, and now I've mapped that to current as a through variable. We began with velocity as an across variable, and now we have voltage as an across variable. So what does this look like as a circuit? Well, we already have a circuit component that obeys the law of I equals something times voltage with respect to time. And that's a capacitor. So if we imagine that the mass acts like a capacitor here, then what we get is that the analogous circuit to this dynamical physical system is just a capacitor mapped in parallel with a current source. So clearly, you would never turn on this current source and leave it on with a physical device, right? Eventually that capacitor would explode and you would see a capacitor juice all over the place. So the same thing is true with a mass on the left. If you kept pushing with the same force, you would eventually see something really bad happen. So either the mass will be going so fast it'll start to violate all kinds of laws and you'll get pulled over by the cops. Or, of course, eventually, in an ideal world, you'd be exceeding the speed of light, which is not allowed either. So this is the very first example. So the mass acts like a capacitance. Let's look at a second example. So now I have a mass, and I'm attaching that mass to a spring. So the spring has some constant K1. So let's first talk about what are the ordinary differential equations that map here. So if we have F is the sum of all forces, so here M1 X1 double dot plus K1 X1. So when we push with this force, that's equivalent to the inertial motion in the same direction plus K1 X1. So we can rewrite this as M1 V1 dot plus K1 integral V1 dt. So I've taken X1 and taken its integral so that I can write it as V1. So we can rewrite this as a current source, I, with the capacitor, M1. And what is K1 times the integral of voltage? Well, we already know that voltage is, across an inductor, is L times the derivative of the current. So we can integrate the voltage to get L times I, and divide through by L to get an equation for I in terms of voltage. So now we can see that the spring actually acts like an inductor. So the first current comes out of this node and drives south through M1. The second current also comes out of the same node and drives through the inductor. So here we have the mass acting like a capacitor and the spring acting like an inductor. Let's look at the third case. So now I'm not using a spring, I'm using a damper. So the damper has some physical coefficient B1. So F again is equal to M1 X1 double dot plus B1 X1 dot. And so we can rewrite this in terms of V, M1 V1 dot plus B1 V1. So now if we push with this force, first of all inertia pushes back, and then second of all this damper is going to push back. So let's go into the twilight zone again. Now we have a current source I. We have our mass M1 V1 dot, so that's the capacitance. But again, now we're looking at how do we dissipate energy based just on the velocity, or just on the voltage. And we actually know how to do that with a resistor. So B1 V1, but we can't just choose B1 as the value of the resistor, because voltage is a current times a resistance. And therefore the current is equal to 1 over the resistance times the voltage. So if our resistance is 1 over R, but the value in front of V1 is B1, then our resistor's value must be 1 over B1. So even though the spring acts like an inductor, we have to invert it to get the inductor's constant. And even though the dashpot, or the damper, acts like a resistor, we have to invert its value to get its resistance. So this is how we come up with, fundamentally from its atomic pieces, how a circuit would be analogous to a physical system. So let's look at an example from the text. This is an example where you can find this diagram and its analogous circuit. So here we have a mass M1. We're pulling on it with some force R of t. And then M1 is connected to 2 dashpots, and one of those dashpots has a mass and another spring in series with it. So we indicate velocity in this direction. And we remember that the sum of all forces is mass times acceleration. So M1 V1 dot, that's the direction downward, right? So we expect that R, which is our force, will be positive on the right-hand side. But then we're going to have negative values that are preventing us from doing that based on these two dash pots. So B2 V1 is going to be pointing in the opposite direction. It's negative. And B1 times V1 minus V2 is also negative. So it's pointing upward. Our second equation, based just on M2, means that we take just the dash pot times V1 minus V2, and then we subtract away the value of the spring. So as V2 moves down, we're expecting that we're going to get a force pulling up. So that's why that value is negative, whereas the B1 value is positive, because we wrote V1 minus V2 instead of V2 minus V1. If this doesn't make sense to you, you can go back and look at the diagrams that we did just on dash pots and just on springs to show how these values can be decomposed. So now we can rewrite this in terms of x1 and x2, obviously. And this is just a change of variables. So some have more dots and some have fewer dots now. But I'm staying with the v's for a reason that will become clear soon. So now I want to isolate the force and put it all on one side of the equation. So once you do that, you can come up with this rewriting. So now we have some current equal to pieces on the right, and then we have the sum of a bunch of other forces being equal to 0. So now we're going to rewrite this so that we'll have it on this page. And I want to consider for just a second that we're actually treating V not as velocity, but as voltage. So we did this with the atomic examples. Now I want to do it with a slightly more complicated example to show how these pieces compose. And R is going to be our current. So V1 dot is dV1 dt, or M1 times V1 dot is going to be some kind of a capacitance, C dV dt. The integral of V2 dt is the same, or is analogous to 1 over L times V2 dt, which is some current, because we know that V is L di dt. So now, again, we see that the mass acts like a capacitance, and that the K is the inverse to an inductance. So if we have K times the integral V2 dt, which we see up there in equation 2, that's 1 over L integral V2 dt. So our inductor's value, that is, what's the value for our inductor, is 1 over K. Because 1 over K is K. So for just a regular resistance, B times the voltage is 1 over the resistance of the voltage. So this gives us the analogous of what our currents are equal to. So in this case, again, we have dashpots that act a little bit like resistances, but this damper is actually inverse to a resistance. So because you have a damper, it acts like a resistance, but the value of that resistor is the inverse value of the damper. That is, R1 is equal to 1 over B1. Okay, so let's rewrite these equations again so that we have them. And now let's draw our circuit. So R is going to be the sum of a bunch of different forces. And so if we use KCL, then the sum of all the currents has to be equal to 0. So if we draw R going into this node and the other currents going out of the node, then R will be on the left-hand side and the other currents will be on the right-hand side. So the first current that comes out, M1 V1 dot, well, we use the mass M1 and we label that this node is V1 because the current through a capacitor is C dV dt. So here the value for C is M1 and the value for V is V1. So we have to decompose just a little bit some of these other pieces to find out that this second current is B2 times V1. And so in fact the value of the resistance is 1 over B2. We also have V1 minus V2 all multiplied by B1. So you can see in the equation 1 we have B1 plus B2 times V1, right? But when we translate that into the circuit, we're interested in the original resistor values. And so we're going to have one current attributed to the resistor B2, and we're going to have another current attributed to the resistance for B1. And so now we're actually going to make this resistor value 1 over B1 here, but we need to create another node V2 because we're interested in the potential V1 minus V2. So that second resistance here divides its current, and we'll see that in just a moment. So this current coming out of V2 will be divided in two ways. So one of the ways that the current in V2 is divided is that it goes through this capacitance M2. And then the other way that the current is divided is that we're interested in the current through the inductor. So K times the integral V2 dt. And remember that K here should be inverted.
All right, so let's talk about this, right? So what's the big takeaway, right? You can, through these analogies, you could create an equivalent circuit, right? Now this is a big idea, because if they're equivalent, they should have the same response, right, to the same input, right? So if your company has you designing something and wants you to build a prototype, but you don't have money to buy actual parts, but you have a bunch of electronic components lying around, you could potentially build an equivalent circuit to test your idea that would have the same system response as your mechanical system, right? Which is crazy. It's crazy, right? Crazy to think about, but you can do it. Now, like I said, I'm not gonna make you guys, I'm not gonna say, hey, here's a mechanical system, give me the circuit for it. That's not what I'm going to do, but I want you to see the utility of being able to jump between systems, right? The same thing goes for a fluidic system, right? You could potentially build a small scale 3D printed prototype of a mechanical system that is equivalent to your sure thing, Kelly. Right? That you can build a small scale mechanical system that would have the same output properties, right, and the same response that other systems have, right? So you should be able to jump back and forth between these modes. Personally, Blake, no, I've not been in a situation where I need to create create a circuit for mechanical system. But the utility is nice. Nowadays, with a lot of our modeling software, what we'll see when we get to Simulink, right, is that it's basically doing this for us on the back end, right? If we understand the Laplace transforms and how to make the models behave in that manner, then we can use software packages that help us do that. All right. Any other questions? No? All right, so what's an electrical system? Now, this is the part of the class where I tell you guys that one of the things that triggers me, right? One of the things that triggers me is when I ask people to define things and they're like, I don't know, it's like a system that has like electrical components. Yeah, that's an electrical system, but like be a little more specific, right? You're not really defining it. But anyway, so what is an electrical system? I'm not asking you guys, I'm just posing the question, right? Well, it's a system that uses voltage and current as the dynamic variables. Okay. Remember, a dynamic variable is any variable that changes with respect to time, right? So for an electrical system, we are talking about voltage and current. Okay. The energy stored by capacitors and inductors depends on the capacitor voltage, E sub C, and the inductor current, I sub L. Remember our equations, right? Remember, we have our ODEs that describe our capacitors, right? Capacitance tells us that the current is equal to C E dot C, right? And we have our inductor equation that tells us the voltage drop across the inductor is equal to L I dot L. We are going to write, in this class, we are going to write all of our electrical mathematical models in terms of the voltage drop across the capacitor and the current through the inductor, right? There are essentially 4 variables that you need to keep track of at any given time when we're making these models. And we'll talk about them more in a second, right? But we still haven't addressed what are we using as our Newton's law equivalent here, right? What is driving this? What physical laws are driving this? Well, in this case, we're using Kirchhoff's laws. Now, this is the point where I want to say we've noticed that everything so far is a first order differential equation, right? First order ordinary differential equation. We don't have any second order systems here. So anytime you have an energy storage element in a circuit, anytime you have a capacitor or an inductor, the order goes up by 1. So an RC circuit is first order because there's one capacitor. An RLC circuit is second order because there's an inductor and a capacitor. Every time you add an inductor or capacitor, you up the order, right? This is, I don't want to say problematic, but you can see how you can get a higher order system very, very, very fast in the real world. Right? So electrical systems tend to scale up in order of magnitude very quickly because anytime you add an energy store, basically anytime you add anything except a resistor, you're increasing the order of the system. So if you have stuff that's not in terms of EC or IL, then we're going to have to use Kirchhoff's laws, right? So what are Kirchhoff's laws, right? How do they make you feel? How do Kirchhoff's laws make you feel, guys? Well, they make me feel very happy. Probably because I'm sick and deranged, right? Something wrong with my brain. I don't know. All right. Kirchhoff's voltage law. Kirchhoff's voltage law says that the sum of all of the voltage drops and gains in a circuit, in a closed loop on a circuit, will equal 0. Okay, so the sum of the voltage drops around the loop is 0. All right, now there's a couple of things we'll talk about in a second with this, but for right now, let's stick with that. So we can see here our circuit, right? We have this simple circuit. We've got a voltage source. We've got 3 different elements. It doesn't matter what they are, right? Doesn't matter if they're resistors or not. We know that our current is going in a clockwise loop here because that's what this clockwise arrow is showing us. Okay, so if I start at here, right, if I apply Kirchhoff's voltage law, I apply KVL, well, this is saying that En minus E1 minus E2 minus E3 has to be equal to 0, right? Because it's in a closed loop. So the sign convention is as follows, right? If you're moving across a passive element from positive to negative in the direction of conventional current flow, right? Or you're moving across a voltage source from negative to positive. So when is it a voltage drop, right? When do we have a voltage drop? A voltage drop is when we go across a passive element from positive to negative, or a voltage, basically, or a source when we go across positive to negative, right? Anytime you're traveling positive to negative and you cross a source going from positive to negative, that is a drop. Okay. Anytime you cross a source going from negative to positive, we consider that to be a rise or a gain. And we don't want to use the word gain because that's reserved for something else. And I'm sure that Professor Bullock and Dr. K go over gain quite a bit in their respective instrumentation classes. Right? So basically, let's take another look at this, right? So we started talking about this a little bit, right? So if I have En, right, this voltage will not have changed by the time it gets to the first one, right? Then we have E1, right? So how much voltage do I have on the other side of element 1?
All of it.
How much of it?
All of it.
Do I?
On the left-hand side of element 1?
All right, so if I have En and then I hit element 1, how much voltage do I have on the other side?
En minus E1.
Oh, on the other side, sorry. I was like,
En minus. All right, so what do I have when I pass element 2?
En minus E1 minus E2.
I think you see where I'm going with this, right? Right. Then we're back at the start. So we have nothing. And then when we cross this, we're back up to En again. That's if you're summing clockwise. What if I wanted to sum it the other way, right? What if I wanted to travel with this red arrow, right? What if I said, well, my current's really going this way?
Wouldn't you just change the signs on the equations we have?
Exactly, flip all the signs. These now become voltage gains through the element, and we have a voltage drop across the source, which is weird, and that's why we don't typically do that way. But just be aware that in certain situations, you might see something like that. All right, cool. And so that's Kirchhoff's voltage law. That's not too bad. We've all seen it before. A couple of times, right? You should have seen that in physics too, right? As well as in circuits, I hope. Does anybody have any questions on KVL? No? Let's talk about the current law. We have KCL, right? What does the current law say? Well, the current law says that the sum of all of the current entering a node has to equal the sum of the current exiting the node. Another way of saying this is that the algebraic sum of all the currents entering and leaving have to equal 0. So we can see in the purple box, I did the box color right this time, guys. In the purple box, right? Or these red boxes, get that crap out of here. All right, in the purple box. Well, if I'm looking at my node here, all right, so let's start off with this, right? What is a node by definition? Well, by definition, a node is any point where we have 3 or more wires attached in a circuit. Do a KCL with a junction that had 2 wires. Sure. You know what you would get out of it? I1 is equal to I1. Right? There's no change. Right? There's no split in the current. Unless we have multiple wires, 3 wires. All right, so what's entering node A here? Well, I've got I1 and I4. Okay, and what's leaving? I2 and I3. So I've got I1 plus I4 plus, I1 plus I4 minus I2 minus I3 is equal to 0. Or I1 plus I4 is equal to I2 plus I3. Right? The sum of my inputs of my current at a node has to equal the sum of my outputs of the current at a node.
Well, I have a question here.
Yeah.
In this case, would I2 and I3 end up like equivalent, or is it dependent on the other passive elements that are like on them?
So they don't have to be equivalent. It all depends on what they're connected to, right? So like we saw in the inductor video, right? Not all paths, once we have branching, not all paths are created equal, right? So there's no reason why they have to, if they split, that they have to be the same, unless the only thing that would make them the same is like if they were both hooked up to the same resistor on the other side, right? Then they would both draw the same amount of current. But there's no reason why just looking at this they would have to be equivalent.
Gotcha. Thank you.
And so typically we say that if you're entering a node, you have a positive current, and if you're leaving, you have a negative. It's a typical sum convention. Any other questions on this before we jump into how to model systems? No, we're good. All right. How do we do it? Right? How do we model electrical systems? Well, the book is going to tell you a lie. Okay, the book is going to tell you that you can do this with a two-step method, which is a lie. It's a lie. You cannot. 2 steps is way too few. Way too few. You have to use a 5-step method because 5 is 3 better than 2. Okay, it's math. It's math. So what does the book say? The book says mathematical models of electrical systems can be derived using a systematic 2-step process. And the first one, you write the corresponding first order ODE for each energy storage element. And then the second one, you use Kirchhoff's laws to do algebra, right? And figure out how to get things in terms of other things. That's yes, but you've missed the other you've missed 3 of the 5 steps, right? And so we're going to use the 5 steps. But the important thing here is in that red box, right? All of our ODEs, all of our equations are going to be in terms of either E sub C, I sub L, E n, or I n. Those are the only 4 variables that we want to see. What determines that? Do I have a capacitor? Yes, use E sub C. Do I have an inductor? Yes, use I sub L. And do I have a current source? Yes, then use I sub n. Do I have a voltage source? Yes, then use I sub n, or E sub n, sorry. We are only going to write our equations in terms of these. And the reason for that is there is a dark alternate universe, okay? There's a dark alternate universe in which people write models in terms of I sub C and E sub L. And then you have to include integrals in all of your equations. And it looks gross and it makes you feel hollow and dead inside. It's not really true, but I prefer to use derivatives, okay? So that's what we're gonna do, okay? There's also another reason for it, and I keep coming back to this, right? And I keep telling you, I swear, I probably sound like some sort of snake oil salesman, right? But all will be revealed after week 5. The reason for doing these things this way is it will be readily apparent when we get a little bit further down the road, okay? So just trust me for now. Just trust me. If it's not, you can have, I don't know. I would say your money back, but I feel like you guys might actually try to take me up on that. I can't fund that. And I'm not going to pull a Michael Scott and say that I'm going to tell it, like, send everyone to college, right? And then, anyway, it's fine. All right, so we're going to use 5 steps again, right? So this time we'll use a circuit diagram. What does a circuit diagram look like? Looks like a circuit diagram, right? We've seen them before. They've got resistors and inductors. We'll see one on the next slide. We have to identify our inputs and our outputs. We need to write our mathematical truths. These are going to be our Kirchhoff laws. These are going to be our element equations for inductors, resistors, and capacitors, depending on what our circuit makeup is. We're going to reduce our equations, we're going to do the algebra, and then we're going to hold off on the evaluation, as usual. So let's run through one together, right? Run through one together. Here is a simple RL circuit. A simple RL circuit, right? I've got a voltage source, I've got an inductor, right? I've got my current going in the direction of clockwise, and I've got my resistor. So what do we do? Well, the first thing we're going to do is we're going to draw our circuit diagram. So I'm going to redraw mine here. Oh, look at that, EN. And I'm going to come across. I've got my inductor. I know, it's basically like it was photocopied right out of the book. I know. I like to draw my current as a line, as an arrow going in the direction. I don't like to typically have it inside, but I will put the plus and the minus here. And I'll put these here just for right now. I don't always, but for this particular example, let's do it. Okay. So, I mean, it basically has everything that we need here. So let's write our inputs and our outputs. What's my input? Somebody.
Ian.
En. Don't miss the ENs, man. Don't miss the ones that have the in subscript. Right? That's the low hanging fruit. Right. What's my output? Based on the things that we've talked about so far in class, what should my output be?
E out.
No, not E out. Here, let me go back.
A magnetic field and heat dissipation?
Let's go back to here. What
No.
should my output be if I have an inductor?
IL.
I sub L. Remember, we are only dealing with E sub C, I sub L, E in, or I in. That is what we're doing. What if I had like 6 inductors in here? Well, then you're gonna have 6 equations with I sub L. They'll all be different I sub L's, like I sub L 1, 2, 3, right? But so just keep that in mind, right? Whatever order your system is, that's how many first order differential equations you need to describe it completely. Okay. This one's first order, right? We have one energy storage, we have one inductor. This is a first order ordinary differential equation system. So our output is going to be I sub L. All right, so what do our truths look like? Well, the voltage drop across my resistor is just Ohm's law. The voltage drop across my inductor is just I dot L. And in this case, am I going to use KCL or KVL or both? Which one? What do you guys think?
KVL.
Yeah. So I'm going to do this guy and say, this is my KVL. All right, so if that's my KVL loop, I should have E sub L minus, E in minus EL minus ER is equal to 0, right? So I have my source, and then I'm subtracting E sub L, then I'm subtracting E sub R, and that's everything that's in here. And that's going to equal to 0. So by KVL, I've got E in minus ER minus EL, or whatever order you want to write it in, it doesn't matter, because it all equals 0. And we said we're not going to use KCL, but looking at this right away, I sub R is not in terms of E sub C, and it's not in terms of I sub L, right? And so that's a problem, because we need everything to be in terms of I sub L and E in, because those are my inputs and my outputs, right? Everything needs to be in terms of E in or IL. So how do I do that? So let me ask you guys this, right? This is still I in here, right?
So would I in just be equal to IR?
I'm going to call that IL at this point. Right. So what is this?
Is that I in minus IL?
No, I'm just renaming it as it goes across. So I mean, the current is constant throughout the entire thing, right? You were correct.
Then IR would just be equal to IN?
Yeah, IN, but I'm going to call it IL because I want everything in terms of IL, right? Because this is actually IL as well. Right? It's all the same. The current through that entire loop is the same. There's no branches, right? If it was a hose, right? If it was a pipe system, you turn on the water, it's going to have the same current all the way through, right? There's no branching of the pipe system. So we're going to call that I sub L. Remember, we want E in and IL. That's what we want. And this sets us up pretty nicely in this loop, right? Because now I can write down my KVL, right? So if I'm going to do this, I'll rearrange it a little bit and say that EL is equal to E in minus E sub R, right? So if I plug in my truths here, I dot L is equal to E sub in minus R I sub L, right? Because we just said that IR is equal to IL is equal to I. And rearrange. L I dot L plus R I sub L equal to E. First order, ordinary, linear differential equation relating my input to my output. That's what we're looking for, right? As Dwight Schrute would say, those are the money beats. Those are the money beats. It's an office heavy lecture today. I apologize for nothing. Okay. You guys have any questions on this? No? Everybody's all right. Okay. Well, since you're okay, you guys can all work in your groups and do this one together. It's not for points or anything. I just want you to work on it together. I'll set up the breakout rooms in a second. Everybody take a second, copy this down. What you're trying to do is derive a mathematical model for this parallel circuit. I'll give you guys a minute to copy it down, and then I'll open the breakout rooms. I'm going to give you guys 20 minutes to work on this and get as far as you can in your groups. I'll bounce around between the groups. Go. All right. There you guys go.
Nice glasses, Dr. D.
Thank you. What's this one? What's that thing? Oh, that'll work. Sorry, I fell into the filter hole there for a second. All right, so what are we gonna do? What are we gonna do? Let's talk about this thing, and then I should probably share my screen. That'd probably be a good idea. Do that. Hey, here we are. So what do we do, right? So most everybody was on the right track. So let's try this out. So let's draw it, right? We got to draw our circuit. We've got this. We're calling this A since it's specifically called out as A, right? We'll call this R2. We got R1, C. And bring this around like this. Ground. I know it's like looking at a textbook. It's amazing, amazing. All right. So we have a current source, right? We have a current source. Okay. And so what does that mean? Well, let's draw this. So now I've got I in here. We were told, we were shown on our diagram that this is IC, and we're calling this I2. Right? That's what we're doing. Okay. All right. So that's the diagram that we were given, right? So is there anything else that we want to do with this? Well, I'll come back and I'll draw something on here in a minute, right? But this is looking all right. So, all right. So what's my input? All together, everybody.
I in.
Thank you. It is I in. What's my output here?
E sub C.
E sub C. Remember, I should never have an output that isn't E sub C or I sub L. All right, if we write down our mathematical truths, we have KCL. All right, let's start with that one. KCL is going to tell me I sub in minus I sub C minus I2 is equal to 0. I know I sub C is equal to C E dot C from my equations, right? My capacitance equation. All right. We also have what? Well, we've got ER1 is equal to R1 I sub C. We've got ER2 is equal to R2 I2. All right. And that's good. That's a good start, right? But I want you guys to notice something here. Given KCL, I have no way of getting I2 by itself in terms of IN and IC, right? I need another equation to do that. And where is that going to come from? And some of you guys were talking about this.
Kirchhoff's voltage.
Exactly. It comes from Kirchhoff's voltage, right? So what's the deal with Kirchhoff's voltage, right? Well, it applies, I'm going to call this LHS for left-hand side and right-hand side. Right? So Kirchhoff's voltage law applies to any closed loop, right? Any closed loop in a circuit. So this is a closed loop on the left. This is a closed loop on the right. And this around the entire circuit, perimeter of the circuit, that's also a closed loop. So out of those three, right-hand side, left-hand side, and the perimeter, which one do you think is most beneficial for us? Meaning, which one gets I2 in terms of IC? Which one gets the voltage drop? I should phrase this in terms of voltage drop. Which one gets the voltage drop across this resistor 2 in terms of the voltage drop across the capacitor?
The right one?
The right-hand side. So that's the one that we're going to use. All right. So our final truth here becomes our KVL, and I'll put A here on my KCL for the right-hand side, right? And that's going to be what? Well, it's going to be negative ER2 plus EC plus ER1 is equal to 0. All right, so let's look at that again. Right? How did I get those signs there? Well, if I'm traveling clockwise here, right? If I'm traveling here clockwise, I'm going to have a voltage drop, right? Because this is plus minus, plus minus, plus minus. It's going to be a drop across R2, but now I'm coming back up this center row, right? I'm coming back up here, and now I'm going negative to positive. Well, that's a gain. I'm going negative to positive across the resistor. That's also a gain, right? So you have to add those two back in. Okay, so that's where this comes from. And now we're ready to go. Now we're ready to go. So you can do this a couple of different ways. Okay, you can do this a couple of different ways. Let's do it. I'm going to do it the way that I think is easiest for right now, and we'll go from there. So I'm going to write my KVL down. I'm going to start with KVL instead of KCL. It doesn't matter. You can do it either way. Right? I just personally think the algebra is easier this way. All right, so there. Well, I know what R2 is, right? That's negative ER2 is. That's negative R2 I2. EC stays what it is, right? Because that's already in terms of EC because it is EC. And this is R1 I sub C. Well, I have an equation for I sub C already, right? Have an equation for I sub C. So this is just going to be plus R1 C E dot C. Okay. E sub C just stays what it is. But I need something for I2, and I2 needs to be in terms of I in and or E sub C, right? Well, from my KCL, I know that, right? From KCL, I know that. Sorry, there's.
Isn't that supposed to be a minus sign?
It is. Caught that. Okay. So there's that. So all right. So we already know what IC is, right? So let's do some algebra here. It's going to be this plus CR2 E dot C, right? So I multiplied through by R2, and then I substituted CE dot C in for IC, right? Plus EC plus CR1 E dot C is equal to 0. Okay, so now inputs on one side, outputs on the other. Do a little algebra, right? So we'll get C R1 plus R2 E dot C plus EC is equal to R2 I in of. There it is. Remember, so I'll say this. Most of the time, for the way that we are setting these up, you are going to be spending a lot of time figuring out how can I get one variable in terms of another, right? Remember, the only variables that we want in any given equation are our inputs and our outputs. That is it. If we see anything else, right, any other dynamic variable like E sub R, we need to figure out how to get it out of there, right? We need to figure out how to transform it into the ones that we want. Typically, KCL helps with that. KVL will also often help with that. There's also some other things that we can talk about in a minute that will help. You guys have any questions on this? Again, I know that you guys have a lot of scar tissue when it comes to this, okay, for the most part. And you can do it, right? You can. You just need algebra and it's practice, right? And it's getting into the swing of applying KVL and KCL. Right? That's what it is. How do you know when you're supposed to use which one, right? Well, if you don't have any nodes, that makes it really easy. You don't have to use KCL. How do I know if I'm supposed to only use one or both or whatever? Half practice, half looking at the situation and using your best judgment. But mostly practice. I'd say it's probably 80 practice, 20 your best judgment. The more you practice, the more comfortable you get. All right. Any other questions? No? Promise. Okay. Well, if that's the case and there's no questions, we'll get to everybody's other favorite topic, which is op amps, right? Everybody loves a good op amp. Everybody. So hey, look, this is an op amp. Sweet, pretty sweet, right? I like op amps because I really like triangles. Man, that's really where it comes down to. Anyway, what is an op amp? If you say operational amplifier, I swear. It's an operational amplifier.
Well, I couldn't say it's not an operational amplifier.
It's a modern electronic device that uses that's used to amplify signals, right? We're trying to gain a signal. You hear somebody say they're gaining a signal, it means they're amplifying it, right? Attenuate means to decrease the signal. So we have a voltage signal. It's coming in. It's really small. We amplify it so we can look at it, right? We never use this. It's not useful in the real world. Let's just throw these out. Except that it's super useful in the real world all the time, because most of the electronic signals that come in from sensors are really small, right? Like millivolt level small. So amplifying them allows us to see really small changes on a larger scale. So why? Well, obvious reason is for amplification, but op amps, depending on how we configure them, can also be used as filters, right? Which is really nice. This is figure 1 right here, and it shows you the schematic of an op amp. They call the positive terminal non-inverting, and the negative terminal is inverting, right? We'll see why in a minute. How do you know if you have an inverting or a non-inverting op amp? Great question. Well, if you find out that your sign comes out, if you put in a positive voltage and your sign comes out negative, that means you've inverted it. If it comes out positive, you didn't invert it, right? So it's all about whether or not you're changing the sign of your signal by going through the op amp. Here is an equation to, all right, so with op amps, let's talk about what we're interested in, right? So this is different than a normal circuit analysis, right? Where we're only going to have things in terms of E sub C or I sub L. In this case, we are always going to be relating the input voltage to the output voltage, because that's what we care about, right? We care about how much we are gaining our signal, right? And so in general, the output voltage is equal to the gain times the differential of the input voltages, EB minus EA. This is in general. And in general, our voltage gain for an op amp is roughly on the order of 10 to the 5th volts per volt. Okay. Now that's all well and good, right? But how do we actually attack these problems, right? Because we want to know how to set up a model for an op amp so that later we can figure out how do I adjust the gain on my system, right? So on the ball with the question, as usual, right? We're going to use ideal op amps. Now, where do you get ideal op amps? You get them at the Ideal Radio Shack. But unfortunately, the Ideal Radio Shack went out of business a long time ago. So all of the ideal op amps are actually in my office right now, right? So no, it's not true. There's no such thing. It's an ideal op amp, right? But we have special properties associated with them that help us in analysis, right? So the input terminals right? So what's the property? First off is that the input terminals draw negligible current. So essentially, this property is telling us that the input current to an op-amp is approximately 0. Interesting. Also, for an ideal op-amp, the voltage difference at the input terminals is 0. So this is telling you that EB minus EA is equal to 0. So therefore, EB has to equal EA for an ideal op-amp. Also interesting. Also, ideally, the gain is infinite. The gain is sideways 8, guys. Sideways 8. All right, so that's great. But I'm not seeing how this is helpful, right? Well, it's all about how we set up our circuit around the op-amp, right? We are going to use a negative feedback configuration, right? And in fact, all of the op-amps in our textbook are set up with a negative feedback configuration, which relays the output terminal back to the inverting terminal. So we're going to basically be using inverted op-amps, right? We're always going to get an inverted signal. This causes EB minus EA to equal 0 to be true. And then all of the op-amps, right, I said that already. All right. So that's great. Let's just do one, right? Let's do one. Yeah, okay, cool. So hey, look at this. That's an op-amp circuit. Let's take another look at it, right? So hey, what do I have? So we said that this is a feedback configuration, right? So look, what does that mean? We've got this here coming down. We have a node here at A. We'll call this A. We've got some input voltages. What about this voltage E sub B? What does that equal to? Why don't you guys think about that? What is that equal to? So what we're interested in doing here is we're interested in finding the expression, the relationship, the equation relating En to Eout, right? How much is my signal being boosted by? That's what I want to know. Okay, all right. So what's EB equal to in this? You guys had to hopefully not guess, but if you wanted to guess, please guess. And if you know, just know and tell me. What's EB equal to?
It could be EA.
Yeah, I mean, we just said that that was true, but I meant like a physical value. So you're not wrong, but you're not entirely right.
0?
0. Why no?
Because there's no voltage flowing in through it. It's at the end of the circuit.
Yes, it's ground, right? There's the ground. It's ground. Connected directly to ground. So it's 0. Well, if EB is 0, and we know that EA is equal to EB, what's EA?
Well, if it's 0, then what's the point of the op amp?
The input to the op amp is 0. That doesn't mean we don't amplify our signal, as you will see. All right, so what do we have here, right? What do I got? I'm gonna redraw this a little bit just to highlight some things, right? I've got I1 right here, right? I've got my node, which is gonna have I sub A, and I've got this current coming out of my node here, which is I2, right? We're gonna leave that for a second. We're gonna leave that for a second. We'll come back though, right? So I'm calling this A here. All right, so what's my input? What's my input to this op amp?
En.
Excellent. What is my output?
E out.
You guys are nailing it. Love it. Love it. All right. E in and E out. Perfect. Mathematical truths. Now, this is going to be a little bit different here, right, than we've done before, because it's not just about the elements here. We need to write down our ideal op-amp truths, right? So for an ideal op-amp, EB minus EA is 0, therefore EA equals EB equals 0. Right? We talked about why that's the case. Okay, what else do we know for an ideal op-amp? We know that that current that's flowing into the op-amp, which we're calling IA, is negligible. And it's approximately 0. We also know that the gain is approximately. That's really not going to come into play just yet or at all today, but we'll write it down anyway so we don't forget. All right, so let's go back to our schematic and let's see what we got here. All right, so I've got a node at A. So I should probably do KCL there, right? I'm going to node at A. So why don't we write down KCL for that? KCL at A. Well, that was just going to tell me that I1 is equal to IA plus I2, right? Yeah, something like that. But wait a second. There's something very intriguing written right above that. What is IA equal to?
0.
So get that out of here. So I1 is just equal to I2. Okay. Okay, I see what's going on here. We have another truth that we didn't write down, right? ER1. There's a voltage drop across our resistor. That's R1 times I1. And ER2 is equal to R2 times I2. Now, can't I rewrite these? This will be more interesting, I think. Methinks. Interesting. So now I have something for I1 and I2. Okay, so that's my truths, right? And basically from here, the reduction is kind of writing itself, right? Because what do I have? I have KCL, right? And if you guys are thinking, well, if I1 is equal to I2, I'll just plug in my expression for I1 and I2 in there, then yes, right? That's how we're going to start this, right? We're going to start with KCL. We don't have to do a KVL for this. And in fact, I would highly recommend that you do not do KVL for this. It's not going to help you do it. So, right, so we've got I1 is equal to I2, right? If I plug in here, I'll get ER1 over R1 is equal to ER2 over R2. Well, that's problematic, right? Because that's not in terms of my input and my output voltages at all. And that's a voltage drop across a resistor. We're going to go back and we're going to look at this again. So dig deep, dig deep. This is going to be a big ask all the way to the beginning of class today. What is a voltage? What is a voltage drop?
The difference.
Yes, it is the difference between what, Jeremy?
The currents.
The voltage drop is the difference between the currents. No, it's a difference in voltages. Which voltages? So just look at R1, right? If you want to know how much voltage drop there is, remember, a voltage drop is the difference. It's how much voltage your resistor is eating.
It's the difference between the voltage before and after the resistor.
Yes, thank you, Sean. And we have EA on this side, right? Because that's how much is right here. That's EA. And going through a node doesn't affect voltage, right? The only thing that a node affects is splitting our current. So we have EA each side here, right? Remember, the only thing that affects our voltage or drops our voltage is when we go through an element. That's it. All right. So if that's the case, what's on the other side of E out? Or
E
R2. I said it. It's E out. All right. Ugh. Anyway. All right. So if this voltage drop is actually the difference between what is coming in and what is leaving, and this one is also the difference between what is coming in and what is leaving, we now have equations for our voltage drop in terms of E in, EA, and E out. So we're closer now, right? We're closer. Okay. And so why don't I put these in my truth, right? ER1 is equal to E in minus EA, and ER2 is equal to EA minus E out. Okay. All right then. So we're going to plug that in for ER1 and ER2. We're going to plug those in. Okay. So that gives me EN minus EA over R1 is equal to EA minus E out over R2. But remember, what is EA?
0.
Right. So look what happens. E in over R1 is equal to negative E out over R2. If I write this to look a little bit cleaner, right? Negative R2 over R1 times E in is equal to E out. That has a similar format to the equation that we wrote down for the output, right? So here's my question to you. What is the gain of this system?
E in, or it's 0, but, or right?
The gain is R2 over R1.
There it is. It's negative R2 over R1. It's an inverting op amp, right? So our gain is controlled by this, right? Because this is what's in front of that term. All right. So what does that mean physically? Well, physically, this means for us that if we want the maximum amplification in this system, we want the largest difference between R2 and R1. We want R2 to be significantly larger than R1. That's what it means. And that's how we increase our gain. And that's the model of our op amp. That's it. Done. This trick with identifying your voltage drop comes in handy a lot with op amps, but also in other circuits as well when you need something in terms of something else. Keep that in mind. Okay? Keep in mind. There is a longer way to do this as well, which involves you having to take the limit as k goes to infinity. You get the same answer. We're not going to do it that way right now, but it will be included in the notes if you are interested. You guys have any questions, other questions on op amps, right?
So our final answer for that would just be the negative R2 over R1 En equals E out.
Yeah. So here, final answer is in blue, right like that. And honestly, if you had left it like this over here, that's okay. But because it's an op amp, right? Because we know it's amplifying, we want to really know what this K value is, right? That's where that's the money beats. That's the money beats. Okay. Any other questions? No? No other questions? Well, if there's no other questions, then.
Are we going straight to the examples posted on the log cloud for next class?
That's a good question. We'll probably do a couple of them. We're probably not going to do them in succession like we did last time. But we're going to do a few of them. Then we're going to move into electromechanical systems by the end of class. So, all right. So that's all I've got for today, guys. You guys can go a little bit early. Next class, more of the same. All right. We'll tie up op amps and then do some examples and then move on to talking about motors and solenoids.
Well, have a good day.
All right, take it easy.
Thanks, Anthony.
Thanks, Professor.
No worries, take it easy.
Will you post the analog video to the Discord when you get a chance, please?
Sure, yeah. If I don't remember, I'll try to do it as soon as I get back to my office so I don't forget.
Okay, thank you. I really like that one. That one was good.
All right, cool.
Actually, the fluid one was pretty good too. Wasn't being sarcastic today, by the way.
Hey, appreciate it.
All right, goodbye.
Take it easy.
Thanks for class.
Hey, Doc.
What's up, Blake?
So I'm actually moving in on Thursday.
Okay.
And I have to make my drive during like this class time.
Okay.
I will not be able to attend.
That's fine. Thank you for letting me know. What we'll do is, since there's going to be participation, obviously watch lecture off YouTube, right?
Yeah.
But there's gonna probably be a Tri-Quizzer tournament problem. So instead, what I'll do is I will private message you a paper to read, and I would like you to just give me your opinion on it and as to how it relates to dynamic systems.
Okay, sounds good.
Cool.
Thank you very much.